You wake up to the sound of your pager ringing. An automated alert has fired and tells you that there's a problem with the production site. You roll out of bed, you open up your dashboards, try to get a sense for what's going on, but you're not worried. This is a system that you wrote. You've troubleshot hundreds of issues over the years with it. This one's no sweat. But this one's different. The dashboards are messy and noisy and unclear about what the problem is. The logs are also noisy, but there's no clear pattern that's telling you what the problem is or even where it is. Your teammates start to come online because their systems get paged too. They start asking in chat, oh, what's going on? Is there a problem with the website's down? Is there a problem with the web server? No, there's a problem. The web server's fine. It must be the backend. But you wrote the backend, and the backend seems fine, or at least it's not the problem. So you get on a conference call. Everybody's talking over each other, changing direction of the conference call, asking questions, not letting anybody finish their thought before moving on, thrashing. And so collectively, now not only are you stuck, but collectively you all are stuck. And now this is not an unfamiliar story to me. I've built services and operated them at Amazon for over 18 years. And I've operated the ones that I've built and worked on, such as DynamoDB and Lambda. But I've also been what's called a call leader, which is somebody who gets engaged when speed is especially important, and maybe the complexity of an issue involves a lot of coordination and just clarifying and just keeping an investigation moving and avoiding distraction. So for the next hour, I'm going to share with you some of the ways that I've learned to get unstuck when troubleshooting and ways to even avoid getting stuck in the first place. The purpose of troubleshooting is to find something, sort of a hidden gem. It's to find something, though, specifically, something that we can do something about. Find the deployment that we need to roll back, or find the underscaled microservice that we need to add capacity to. Notice these aren't necessarily the root cause. They don't tell us why the deployment had a bug in it, or even what the bug was. It doesn't tell us the circumstances that led to the service being underscaled and why we needed to add capacity. We'll, of course, follow up and figure out those circumstances and the bug and the nature of all of the root causes that led to something getting through and being a problem in production. We're just looking, though, to make sure the badness goes away, and then we do the rest later on. Later on, we'll find out how to learn and share best practices by doing kind of a root cause analysis, sharing that broadly, finding those common patterns and improvements to the underlying systems that everybody can benefit from. But at the time, we just need to make the impact stop. Now the challenge is, if we're dropped just into a middle of an outage somewhere, we don't automatically know where to look for the problem. We don't even know what the problem is to look for, so we don't even know what we're looking for. Imagine you're dropped into a desert somewhere and you're tasked with, hey, go find the buried hidden gem, the hidden valuable thing. Well, again, you don't know where it is. You don't know what it even is you're looking for, a hidden valuable thing. How deep is it? What direction should I start off in? No idea. And troubleshooting can feel a lot like this sometimes. Throughout this talk, I'm going to share a bunch of observability tools and how to apply a set of troubleshooting practices. The tools will be in terms of CloudWatch because that's what I know best, but you'll be able to draw parallels with whatever observability toolkit you use wherever you are. But the techniques, to me, these techniques are the things that will make you be cool under pressure. These will be a mix of mechanical tactics, like how to navigate between things and look for connections and leads to follow. But there'll also be a bit of strategy, like how to think of the troubleshooting process, what the goals are, and how to think through checklists of marking things off, ruling things in and out. So cognitive strategies. And I think it's great to talk about tools and techniques and everything, but troubleshooting isn't something that tools do. Troubleshooting is something that tools help you do. And as long as that's the case, then the most important thing that we need to tune and tone is our own thought process, our own ways of thinking. So that's why I think it's important for this talk to spend a decent amount of time doing some thinking about our thinking. So let's analyze the human thought process that's involved in troubleshooting to figure out how to make things move faster when there are outages. The talk will be in 4 acts. We'll talk about my strategy, the 5 causes, sort of a grand unified theory of troubleshooting. We'll talk about navigation and how to get from point A to B to C to D until we get to the root cause. We'll talk about the telemetry that's needed, the thing that needs to happen in the application to even be able to understand what's going on and where. And then we'll talk about how to investigate even faster into the future. So now you've all done troubleshooting before, but I think it's helpful to step back and think more formally about the things that you were doing while you were troubleshooting. Because we do a lot of these things intuitively. I'm sure a lot of these will make sense and be relatable, but let's put some structure around that thought. Now you might think that the only one question that there is when we're troubleshooting is, I need to find out what changed. Something changed, let's figure that out. Or sometimes I hear people say this in terms of what failed. We need to find the thing that failed. Well, when you think about it, a failure is sort of a spontaneous, unplanned change. So you could say it's all just a change. But I think this goal of trying to search for what changed or what failed to be true but imprecise, too broad to be a helpful way, a helpful thing to serve as an objective of my final thing that I'm searching for. During an outage, okay, if you ask what changed, everything changes. All your metrics are going crazy. Your logs are filling up with all sorts of spam that is unrelated, more of an effect rather than the cause. So if we just think, well, what changed? We're just going to be flooded and maybe even get stuck from the overwhelming amount of information. So if that's too broad of a goal, then what should our goal be? I'll make a bold claim that the goal of incident management is to find out which of these 5 causes are responsible for the incident. When you're investigating an outage and working, collaborating across your team, you all, if you're doing useful work, you're looking for these 5 things or communicating and sharing information about these 5 things. It's a fairly bold claim to say that it's these 5 things, but I think it is. So I posit that every outage boils down to these 5 triggers or systems. Either you made a change to some part of the system, like a code deployment. The inputs of the system changed, like a traffic spike from a particular workload. The input, I just said that you ran into some limit, like running out of capacity, hitting a scaling tipping point. Or a component of the system failed, like an EC2 instance, your application crashed on an single EC2 instance. Or something you depend on failed, like a dependency of yours, a different microservice, and then you need to shift the investigation to look for the needle in a different haystack. Again, so these aren't root causes, these are just things that we're looking for to make the problem stop. And so the first thing we look for is what changed. Whether we made a change, not just anything that changed, whether we or an automated deployment system made a change. Code deployment, infrastructure change, configuration change, database schema change, feature flag, or more difficult to detect things like maybe you just discounted a product in your product catalog so it has a pricing error and now everybody is trying to buy that product that's way cheaper than it's supposed to be. Those are also changes that are hard to detect. So we look for these because we can mitigate them quickly. If there's something that we or a system changed, we can undo that change or deal with the effects of the change by undoing it through some other more complicated process, but that is still the thing we do. Okay, second is to look for a change in inputs. So this means that maybe the request rate increased to our web service or website. Or maybe the request rate didn't go up, but each request became more expensive to serve. Like each request was doing a more expensive query and now it's more costly. And so if we can figure out the source of that change, the change in the workload that changed, then we can block it. Because the reason is for these kind of workload changes, sometimes if we're getting overloaded, the whole system, the latency of everything gets so slow that it becomes nobody's happy. Like the perceived availability from the client can go down. It's an overload. And so the tool for dealing with that is blocking the traffic and load shedding to make the excess traffic be the thing that suffers and everybody else who is let into the system has a good experience. Great. But now we don't only look for a traffic spike. You know, we also, when we see that callers change something, we're looking for things that we can do to mitigate. So we should also look to see if one of the other 5 things are applying. Like maybe while we're working on chasing down where the increased traffic is coming from, because that's only a theory in the moment, we should also check our scaling to maybe we should ramp up our auto-scaling groups or something like that, scale up at the same time. These are parallel actions to mitigate. Okay, let's say we breached some limit of some kind. Well, we should probably scale up. If we think we're out of CPU or something, we should add capacity. Easy. Now, this rarely happens spontaneously, so we should also check for bad inputs that we can kind of go after that in parallel. Block the bad inputs while we're working on mitigating scale up. But we don't want to get over-rotated on checking for bad inputs because maybe we just hit a slightly higher daily peak than yesterday and that tipped us over to a scaling tipping point. And so it would be, we don't want to go too far down checking for the bad input because it's really, in this case, hard to tell that we're just a little bit higher than yesterday or something. Now, scaling, running out of compute resources isn't the only thing you can run out of. Maybe you bumped into a certificate expiring. That's also, you ran out of the seconds left on a certificate. That's an immediate outage. We need to refresh or renew that thing. Now, I've seen services run out of things because, again, in terms of what else to investigate that's related, a change. There might have been a code deployment recently that caused each request to be slightly more expensive to serve. So we, again, ran out of a limit, but we should also look for changes that could have led us there. Now, an interesting one that you might not be so intuitive is if a dependency of yours, a remote service call, becomes slower than before, that can actually cause you as the client to run out of, say, concurrency. Like you could run out of threads while all of your threads are tied up waiting for that one dependency. And so those threads aren't free to do the other work that didn't even need the dependency. So they're all things these are all connected. Fourth, we look for component failures. These are things that are physically or logically separate that can fail independently. So we should see if our application, based on our application metrics, whether we're being more successful on one thing or another, like one EC2 instance, one availability zone, one pod, whatever. Look for things that can fail separately to see if your application is being slower or failing more on one thing than another, because the remedy is just to stop using the thing that isn't performing as well. Just take it out of service, out of the load balancer, out of DNS, whatever, to shut it off. But we're not done when we find that. We should also check to see if a component failed because it's getting overloaded. Maybe it received a certain workload, a certain request that's a poison pill. We should look for more changes because maybe it failed because it was the first host to receive like a new kernel version or something. Or when we find a dependency failure, like we make a remote service call, and we might call a database or a cache or some third-party service, well, we should shift our investigation. We should look at the dependency instead of ourselves. Now, we also don't want to get over-rotated here, because sometimes it may look from our perspective like a dependency is failing, but it's actually us that's failing. We're failing to call the dependency. Maybe sometimes, let's say if I'm a service that's overloaded and I call a dependency, it might look like the dependency is slower, but that's actually me. That's me being slow. I'm out of CPU. Everything is slow. So I don't want to get over-rotated on the dependency. Or it could look like errors are coming from the dependency, but it's actually, I started calling the dependency wrong, bad arguments or something. And that can present several different ways. So I actually have a deployment of mine that I need to roll back. Or bad inputs. Yeah, I might be calling the service wrong. I may be getting throttled. It might be over a quota. So I don't want to over-rotate on a dependency, but I do need to really shift my investigation. Another way to express these 5 causes, these 5 things to search for as sort of a checklist, is as an algorithm. It's sort of a program. We can look to see if we changed it, if the inputs changed, breach limits, et cetera. And the nice thing about the algorithm style is that when we can, each cause maps to a mitigation we can do. If we change something, undo the change. But this isn't all. Okay, we're still building up the algorithm. We also need to loop this thing. We need to keep going until recovery happens. Until recovery happens, we just keep running these steps. They're non-blocking, so we don't just wait for one thing to complete before we continue chasing another part of the investigation. It's sort of a forking algorithm. And the algorithm is recursive. We're focusing on one kind of microservice at a time, and we can shift our attention. So the last line there, if there was a dependency failure, we should run this same algorithm, the investigate algorithm, except this time with the service's dependency in focus. And again, it's all forking, all parallelizable, all non-blocking, so that we can actually get all of these avenues of investigation going at the same time. So the nice thing about this algorithm is that it's parallelizable. It's an activity that matches how you and your team are doing your troubleshooting anyway. You're breaking up, you're saying, hey, you look at this, I'm looking at this, and then you're communicating and sharing findings with each other. So the nice thing about focusing on these 5 causes as sort of a checklist is that it draws our attention to the most likely culprits, the categories of things that we know it is. They link to each other, so as we find information about one thing, it points us, rules in or out, or maybe somewhere in between all the other causes. It also focuses us on mitigation. Each of these maps to a thing that we can do to make the impact stop, roll back a deployment. And it also helps us keep from having tunnel vision. You chase these down. I guarantee when you're troubleshooting, you are following these like breadcrumbs, following the scent of these things. But it's easy to get just over-focused on the thing that you're looking at now. So having a checklist helps us pop out of that and think, oh, I need to go check to see if we are running out of anything right now. So in other words, by following and chasing down these 5 things, it helps us from getting stuck. Okay, less talk, more action. I need to show you this. You need to see it to believe it, maybe. Okay, so let's go through the full flow. I'll go relatively quickly with a demo, and then we'll actually kind of replay parts of it, and I'll explain what I was thinking a little bit more, or the tools I was using a little bit more. So I'm going to troubleshoot a real set of web services that I made. These services, imagine, are a robot as a service. So this made-up service, it's a real service, though. I created it. Provides APIs to provision robots and command them to go send them instructions and schedules and stuff like that. So the robots will work for you. Great. That's all you need to know. Let's go. As I troubleshoot, I'm going to fill out the checklist of the 5 causes. I'm looking for a change in inputs, change we made, change in inputs, whether we ran out of something, a component failure, and a dependency failure. And each of the Y and the N mean yes or no. So yes, I think there was a change that we made, and the number next to it is sort of a confidence, like, oh yes, an 0.8 means I'm pretty sure that we made a change. I have a good indicator of that, versus no, I don't think it was a component failure, but I'm not totally sure. I'm 50% sure. Okay. So I got paged. Like I said at the beginning of the talk, you should have probably responded to this incident faster. I already burnt a few minutes. So it got paged to alarm that's going off. I can see it's coming from an application load balancer. So let's figure out why. So I'm going to scroll down to the bottom of the alarm page where I'm looking for a runbook. I should have linked myself to a runbook or a dashboard as a starting point, but I didn't do myself any favors. I didn't leave those breadcrumbs of where to go next. So I'm going to rely on things that are built in instead. So I'll scroll back up to the top and use this new Explore Related feature. This is new as of last week. This opens a side panel, and the side panel follows you around the AWS console as you investigate. It shows you related resources to help you navigate to the next place to look at, and when you scroll down, it also brings you telemetry about that AWS resource that you're looking at. So here, already, I can see and start ruling in and out some things. I can see the request count. It increased a little bit, but that is so little that it looks like it might just be a cause or an effect rather than a cause. So I'll say no, probably not the trigger, but maybe I'm not totally sure, 50%. Keep scrolling around. We can see there was no increase in 400. So if we were throttling a particular workload, rate limiting one of our clients, those would show up as 400s. Okay, so I'm building confidence that it's not a change in inputs. Looking at other metrics, nothing particularly interesting. Let's keep navigating. We found everything we can here. Let's move on, get more data. Load balancers have target groups. Target groups have metrics of their own. So I have more information. The unhealthy host count didn't increase. So this means I'm probably not crash looping. My application isn't crash looping failing health checks. The fact that the healthy host count didn't increase means I'm not reactively scaling up. So that is helping to rule out that I'm not running into something. Or if I am, my auto-scaling rules are broken. So I'm not sure, but it seems like it. So I'm ruling things in and out, using the information that's right in front of me kind of opportunistically, in sort of a greedy algorithm in the computer science parlance. Nothing really here. Let's keep navigating. What else can we look at? Well, connected to those target groups are the hosts behind it. And I'm seeing that those EC2 instances, no interesting change in CPU at all. So more evidence that I'm not running out of things. I can also see the EC2 down below, the EC2 status health checks. That's going to be down below. Aren't failing, so there's no underlying physical problem underneath my virtual machines. Keep rolling down, so ruling out a component failure a bit. But now I'm kind of running out of things. I've kind of already looked at a bunch of infrastructure-related metrics. I need to see more about what my application is doing. I'm kind of running out, okay, it's not CPU. I need to get a little bit higher fidelity about how this is actually impacting my application. So what I've done here is clicked from an EC2 instance into the application running on the EC2 instance. So CloudWatch has realized that there's something running on that piece of infrastructure that's actually emitting custom metrics, its own application level metrics. And so I can see the metrics that my code is actually sending. Just as proof, I can scroll down and you can see suddenly, now these are URIs that are in terms of certain APIs, like put, bot, schedule. That's something only my application knows about. So it has found things that my code are doing just through this navigation. Okay. Nothing I'm really gaining from this, I'm just showing you kind of what this is about. But also services, my infrastructure, my code on those EC2 instances are running logs. And so here we've brought you a view of a summary of what's in the logs. If you were to just open the logs, you would see a ton of unique lines. Every log line has some unique request ID, timestamp, and everything. This uses machine learning to do a pattern query in CloudWatch Logs Insights to summarize and squash. So you can see with the counts, this squashed 88,000 lines that were all unique into one, just so you can see the sense of what's going on. But now notice I'm not seeing anything interesting here. So what I'm kind of now coming to the conclusion to is that I'm looking for a needle in the wrong haystack. So that's why I filled out that maybe it's a dependency failure. I need to look somewhere else. So let's look somewhere else. To do that, I'll scroll back up to the top and look in application signals. This is another part of CloudWatch that goes more into the application's own instrumentation and measurements. So if I go in there, I can see we have detected that there is an actual service, microservice, running on those EC2 instances by joining up some infrastructure information and indexes. I'll explain that later. And so this is showing me that there is a spike in faults. So I need to understand what those faults are coming from. So I can click on that spike and it pulls up this investigation side panel and it shows me some spans or traces that I can click on. And now I can kind of see an overall picture of my distributed system. I'm into trace land now. So I'm now looking at a trace as it flowed. I was looking at the bot service on the left, but I can see the actual problem is more likely in the bot forge on the right. So I need to go, I was looking in the wrong haystack. Let's go look at bot forge service instead. That's the thing that you configure, it configures and builds robots. Okay, so let's click on that and go back into application signals just for that robot. Excuse me, just for that microservice. And I can see it doesn't have dependency failures. So now I've cleared, now that I've switched to a different microservice, I've cleared out that kind of checklist. I still have the old one saved away, so I can go back to it if I need it. But I've cleared it out, and it doesn't look like there's a dependency problem here, because I've probably found the right thing. Keep rolling things out. I can look at the APIs. This is sort of an automatic dashboard that application signals generates. And already I have, per API for the Forge service, a couple of things. I can see there's no request rate increase to this API, so that's not happening. But then over on the right, I can see that there are faults. So now this has shown me that there is a problem. Obviously, this service API seems to have a problem, but it doesn't tell me what the problem is. So I need to break down those faults by some other kind of constituent part. And in this case, this button, kind of looking at top contributors, breaks down those faults by some dimension, like per instance ID. So my application is failing exclusively on one of the EC2 instances. So what should I do if my application is failing exclusively on one thing, one piece of compute or component or availability zone? Should take it out of service. Just remove that thing. Exactly. So do that and I'm done. So we have actually solved the troubleshooting issue. But now I'm in bonus round. So I followed that metric back into that EC2 instance just to learn a little bit more. Again, impact is stopped. I already removed it from service. Let's just look more. This new Explore side panel in CloudWatch, you can get into it anywhere in the AWS console. Here I am in the EC2 console looking at that. From any metric, I can say, okay, Explore related. And it'll pop open the side panel again to help me troubleshoot. Back on the EC2 instance, I can find the logs that are coming off of that EC2 instance just by clicking. And now I can see it'll run the patterns. Now, again, I'm in a different microservice than I was looking at before. And here I have the error. It says that there's some race condition, some thread pool state is wedged. Great. Now I figured out what's going on in this microservice so I can figure it out, find the bug later. But the impact is stopped. So we mitigated impact. We even did a little bonus finding out the bug. Am I done? Should I just go back to sleep now? I wouldn't. Yeah, I wouldn't. It doesn't sound like you would either. So I would say, well, why though? Like, why did it fail on that host? I need to know a little bit more to make sure that it isn't about to come back. What if this EC2 instance is the first one to come up with a new kernel version, and we're about to cycle the whole fleet? What if I just did a code deployment, and we're doing that, rolling that out incrementally, and it happened to affect this host, and it's about to do the rest of the EC2 instances? That would be bad. So my algorithm's broken. Said while it's down, while we still see impact, I need to keep investigating. It's actually a little different. It should actually be while it's down, or if I'm pretty sure that it's not going to come back. Whatever, this is subjective. This is whatever amount of confidence that I need in this ambiguous environment to decide how sure am I that I can go back to sleep. Great. Okay, so now we've done that. Let's move on and kind of unpack a little bit what the important things behind that tool. You might not use a ton of CloudWatch. I'm going to unpack what the tool was doing so you can find that in your own tool. So a key part of troubleshooting, a key tactic that I was doing is I was navigating a lot. I was navigating really quickly. And I was looping. I was investigating, seeing what I could see, and then navigating somewhere else, seeing what I could see. It's like in the desert. At any point where I have some metrics, some terminal that shows me metrics and logs and trace information, and I'm gleaning what I can, checking things off the checklist, but then I'm navigating. I'm looking for a place that I can look next. There's this idea in UI research that was a term that was coined by some Xerox researchers in the late 80s and early 90s called information scent. And that's that a web page or a user interface gives off some sort of scent, and the user is trying to sniff out an answer. And so they're following their kind of information sense of smell to figure out whether this part of the UI or this other page will give them their answer to their question. And so that's what I was using. I was using that explore panel as much as I could to get a sense, like on the right, get a sense for the smell, what's here. But then I was also using the navigate part of it to sniff out the next place to go, the most likely next place to go. And the trace UI at the top gave off a lot of aroma in a good way because it was showing me what's connected and their health information kind of all at the same time. So that's one thing that's handy about that kind of connected explore widget. Mapping out my journey, I started from an alarm that was derived from a metric that came from a load balancer. So I went there, I ruled some stuff out quickly, I moved on, ruled some stuff out quickly, moved on to instances, ruled out things like not running out of CPU quickly, moved on to the application. And so each time I was being opportunistic, sort of, again, a greedy search algorithm where you're kind of going wherever you think it's most likely to do. Not always optimal, but I didn't get stuck. Notice this whole time, I went to logs. This whole time, I didn't actually switch tabs. I didn't have to remember to type anything in. I didn't say, oh, okay, I'm here at this place. I need to go find the log group name. What log group are my application logs coming from? That's sort of been the problem of navigating and looking and getting that information sent prior, was that I had to use my brain. I had to use my kind of cycles in my brain to remember how to get to the next place, how to get to logs from a load balancer. This was all just clicking. All clicking, not typing. I didn't use my keyboard. Didn't copy paste any ARNs. So that's the key. We want to make that movement and navigation seamlessly. Now let's talk navigation, or connectivity, which was necessary in order to have that clicking thing, the click only. With good connections, we can see where to go next without having to use our brains. We can just see which of the outbound paths is the most lucrative. We don't have to invent and imagine new places. And so there are a few types of relationships that we were using there. So in the infrastructure plane, where we went from kind of load balancer to host to target group and everything, I'll call that the infrastructure plane. And these were relatively simple connections for us to make. These are just calling describe APIs in AWS. Load balancers have target groups, have instances. That's how we're establishing those connections. Or even this IAM role, that's an instance profile of those EC2 instances, has permission to talk to this DynamoDB table. Okay, that's a configuration time relationship, and we pull those in. But then I jumped up sort of into a different realm, if you will. I went into the application plane, where I knew about suddenly my code and the bot service and how it was doing and what it was logging. So how did we do that link? How did we build that link? Well, we actually used the telemetry as sort of a join key. So we know that this instance has this instance ID, and also CloudWatch is getting metrics. It's getting telemetry in from the application, logs and metrics from the application. And we know, we can see when we receive that telemetry which EC2 instance that came from. So we use the telemetry that's coming in from the compute to build that link from instance to other telemetry that you should look at, just indexing it. And in OpenTelemetry, a lot of people use OpenTelemetry to send their data. There are actually some correlation fields you can fill in, some attributes that say, what infrastructure is this on? And the whole point of that is to be able to do this navigation between planes and types of telemetry and navigate. So it's very important to use that. In CloudWatch, we get to do it automatically for you because we see what compute your API calls are coming from, so we can link that automatically. Okay, so now we've gone from the infrastructure plane into the application plane. How do we get around once we're in the application plane? Because once we got there, we were moving really quickly from microservice to microservice, covering a lot of ground. Well, to do that application to application or microservice to microservice technique, there were actually two ways that we do those relationships, that we establish those. One is tracing. Tracing is a very important thing to do, I think, in instrumenting applications. It's where when anybody gets a request, any microservice participating in some unit of work in a distributed system is participating in a relay race, where you're passing a baton. For that request, it's a relay race. And so when you run a relay race, you pass the baton. So if I'm the bot service stack, I pass the baton off to the bot action service stack. The baton is a unique trace ID. And you propagate that along. So everybody knows that when they're working on a request, what the purpose of that request is. And then they log that out. Now the other important, in order to establish relationships, we have to send all of those pieces of the trace called spans into some central place, like AWS X-Ray. And then it can stitch those together, show you a trace, build that whole service map for you. There's another way that AWS application signals builds these relationships without tracing even. And that's through semantic conventions, which are also an important part of OpenTelemetry. So when a service receives a call, it's important for it to emit golden signals. Like, how did I do when I was working on this request? And so that table on the left is sort of a record. Imagine this is just an index into metrics. I have a metric called bot service latency. Great. But I also should be writing down how my dependencies are doing from my perspective. So when bot service calls a service, it should record that latency separate. So we can do that breakdown. And so we can stitch this together just from conventions and from this metadata. So we look at here's how. We look at the table on the left, the service metrics. We say, okay, we have bot service. I'm going to create a node. Bot service shows up twice in the client metrics table, so I'm going to make 2 outbound edges. Those edges are pointing to 2 other remote services, so I'll draw those 2 as nodes. And then we'll continue doing the lookups. So say, okay, bot actions is actually a service that calls another service. This time, bot actions and schedules call the bot forage service. So now we have our topology, all without tracing, just sending data with following conventions of naming to the same place. So using infrastructure and application topology, we've navigated from an alarm to the metric the alarm was about, through the infrastructure plane, up into the application plane, through the application plane to the dependency that was having the problem, and then down just kind of in between those 2 planes where we're measuring the application's success rate per piece of infrastructure. All without having to click, only clicking, without having to type, without having to remember and use our brain we were using our brain for the important thing of checking things off and thinking about what we should look for. We weren't thinking about how do I go do that fact-finding mission to figure out the logs for this thing. We were just following information sent that the UI was giving off. Now, there's one other relationship that helps us navigate that I haven't talked about yet, and that's manual instrumentation or manual connections. So what if I had just done myself a little bit more of a favor? In this alarm page, remember how I didn't really know where to start off from because I didn't fill in a link to my runbook? What if I had? What if I said, hey, okay, whenever you get one of these alarms, let's go look at the application layer. Let's start there. So I'll go to the application signals service map where I can see what's connected to what, zoom out, and this shows you left to right, the client on the left and the deepest dependency on the right. And now I can see, okay, sure enough, all the way on the right, bot forge service is my core dependency that's failing. Again, it's giving health indicators is the coloring, so it's red. Click on that, now I'm in application signals. Okay, sniffing around, what should I see? I can see the service operations are failing, see that there are some faults. I don't need to look at spans because I already got here through the topology. So I'll just go to top contributors to break down that failure metric. Boom, on an EC2 instance. Pretty fast. Once I got to that application layer, I could move really fast compared to having to go through these side roads. So this is just showing me the application layer of instrumentation is so important. It's so important to have good application instrumentation because I can move faster. It's like I'm driving on a highway between components instead of having to do the side roads in the infrastructure. I still need the side roads. I have to be able to navigate in order to, otherwise I get stuck because I don't know where to go. I can't get to the highway. Or I need to be able to drill down and find the problem with the infrastructure. So all of this navigation is important, but in terms of troubleshooting, having that application layer instrumentation broke down the right way is very helpful. And we only got to the conclusion because we could see how the application was performing. So what do we need to make sure we put in place ahead of time to make sure we can do that during an incident? Well, that's instrumentation. We need to make sure we have the right instrumentation. Look at this code. This is a product info service. This is like returning, I don't know, from an e-commerce site, returning product information. If something went wrong with this code, how would I even understand what's happening? Like when something fails, how would I know which product it was for, which customer was sending the request? How would I know when the request fails whether it was a cache hit or a miss? Or how would I know the latency or whether the type of failure that happened when we talked to the database? Or how long database queries take and how many rows are returned? How do I know from just this code? I don't know anything. And so what we need is instrumentation. And now this has actually gotten a lot easier over the years. Thanks to OpenTelemetry automatic instrumentation. So this is fully instrumented code, except I've actually only added 2 lines. I added a little bit of information that only I could know about my application. Like I can't, at least so far, it can't be done automatically. But all the other interactions, like the requests that came in, well, the outer framework that does the web requests, they have like Flask if you're in Python, Spring if you're in Java. These will have plugins with OpenTelemetry. So they'll start a span and end a span for you and fill in a bunch of details like which API it is, time, how long things took. Client frameworks do this too. So database drivers will also just record client spans for you to say how long the database query worked. Sometimes it'll even tell you what query it was so you can troubleshoot kind of problems with databases. It's pretty nice. So automatic instrumentation, all you need to do is pull it in as a dependency. You can side load it in some environments, and it's pretty nice. You just get a lot. For all that instrumentation you can get automatically with the right framework integration. If you have your own framework inside your company, do the framework integration once with OpenTelemetry, and then everybody in the company gets the benefit. So what does instrumentation produce? What am I even talking about? Instrumentation about web requests produces spans, or units of work, not just web requests. Instrumentation from an application should produce spans. Spans include a bunch of things about each unit of work. It includes things about who made the request, who are we doing this for, or what's their client IP address, what's the trace ID that this is part of. It includes infrastructure information about where is this running. Like I said, we need to be able to know whether the application succeeds or fails in an availability zone or each piece of compute. So we need to write down for this request which one it was running on. And also it includes a lot of timing. Like, was this a cache hit? How long did the database query take? That sort of thing. So a few categories of things. A different way of categorizing these, you could say it's measurements. It's like how long did these things take? And it includes attributes of things that I can break down those measurements by. Now, what do we mean break down measurements by? This is actually a key idea. Well, at one point in the investigation, we were on this graph. We knew the service, we knew the API, but we saw that there were faults. But we didn't know where the faults were coming from. we needed to be able to zoom in and break down the faults by something else. Remember, and that's what found the instance ID, where all of the requests that were failing came from one of the things, one of the components. The concept of observability that we were taking advantage of here was called dimensionality. Dimensionality is the idea when you're measuring things, you want to be able to break down that measurement or that metric by things, by other dimensions. Breaking it down by service or API or EC2 instance ID. We want to be able to break down requests per customer or per bot ID or per client IP address. Now, this instrumentation is really important, but like how do I plot those things? How do I actually display them? Because dimensionality, this idea of breaking down a measurement by a thing, comes with this kind of tricky side of cardinality. You have only a few services, so plotting errors per service, per microservice, that's one line per microservice, not going to be very expensive. But when you start to break down some measurement by a thing that there are a lot of robots, a lot of calling IP addresses, well then that can be, I have to think about how I'm storing that instrumentation. So what should I measure? If I have to make trade-offs about whether we need to be able to break things down a certain way, what should I measure then? What should I bother instrumenting in my application? Well, I say that we should measure things that can fail separately. If something can break, or if we need to be able to inspect something by that thing, then you have to measure it independently. You have to label it, or else you won't be able to operate. Like, how would you operate if you're not measuring the failures per EC2 instance or availability zone? How will I know if one's broken? If I'm not measuring success and failure or latency by deployment ID, code deployment ID, how am I going to know if my deployment broke it? Or if I'm not if I have a traffic spike, how will I find out where it's coming from if I'm not measuring traffic by caller, by workload? You can't. You have to infer it through some other telemetry, but the quickest way is just by writing it down. But where do I write it down? I was showing spans, but open telemetry, we have these three pillars. We have metrics, we have logs, and traces. So what should I put it where? Because this could get out of control cost-wise. Well, here's my rule of thumb. Here's my suggestion as a starting point. Metrics, if I'm instrumenting, again, this isn't where I look at things, this is where I instrument. If I'm instrumenting my application, I'll emit metrics for things that I'm measuring periodically. Like if I'm measuring CPU, I'm pulling proc stat, or what other kind of network-related things. If I'm EC2, like instance-level system stuff, pulling periodically, metrics. If I'm writing down stuff like debug, error, info, kind of information about processing requests, put it in logs. Everything else about when I'm serving a request that I might care about, put it into a span in the trace. That's just my rule of thumb about where to put different instrumentation as a starting point. And the nice thing about this is depending on what observability tool you're using, when you put things in the span, that's kind of superimposed into all states at the same time. I'm maybe getting a little too quantum there, but if you write things down in a span in CloudWatch, well, those are in logs now. As of last week, those spans actually show up in CloudWatch logs. And so you can break things down and use log analysis tools. Since they're in CloudWatch logs, you can have CloudWatch derive metrics from those. So by putting them in the span, then you can, when you need things to show up into any different place, whether it's as a metric on your dashboard or a log, you just do that with configuration rather than having to change your code when you want to see that data differently. And what I mean, so I was kind of saying how breaking certain things down by IP address could get expensive really quickly. Well, that's not true if you're putting it just in the span. It doesn't incrementally add much cost, because what you can do is write stuff down in the span, which is in a log, and then configure like a contributor insights rule. Contributor insights takes something from your log and measures it and breaks it down, but only keeps track of the top 100 per minute. So this way I could plot requests per client IP address without having a metric for every single client IP address, because that would explode and have a lot. If I don't feel like writing down a contributor insights rule, by just having them in the span logs, then I can break things down with a query on the fly. I can say break down the traffic per IP address and just run that as a log analysis query instead of trying to have it as a dashboard. I might wait a couple more seconds for it to load, but if it's an investigation, I can afford that. If it's on a dashboard, I should probably have that as a metric. Now, if you haven't looked at AWS X-Ray in a while, I just want to point out it has gotten some pretty major upgrades in the last couple of weeks. Now you can send all of your spans without needing to sample because X-Ray now just puts those into CloudWatch logs. And it does that actually at a different pricing structure than it did before, even in CloudWatch logs. So this is a pretty compelling approach now. It also accepts, X-Ray accepts traces and spans over the Open Telemetry Protocol, OTLP, directly. So you don't actually have to do data transformation and have a bunch of SDKs that are specific to X-Ray within your client. And CloudWatch Logs, also making this even better, CloudWatch Logs also supports indexes now. So I can define an index on my logs to make it so that if I need to query my spans by, say, robot ID or something, I can put that into, configure that on my CloudWatch log group, and then the query is to look things up by that, or like by span ID, that's by default. Those are quick, and those are actually, indexes in CloudWatch Logs come at no additional charge. So it's included in the price of CloudWatch Logs. You can define up to 5 indexes or something as of right now. So now just to give you a taste of what I mean by this ability to zoom in. Let's say, for example, I'm looking at, I have a customer complaint here, where a customer said that a robot isn't following the schedule. The customer says, I configured a schedule for my robot, but it's not moving. And actually, the schedule has now disappeared from the system. So we must have messed something up, because we said we let the customer configure a schedule, and the schedule disappeared. Not good. So to troubleshoot this kind of thing, I need to look in into the actual customer interactions to see where we messed up. I need to see how we performed in each customer interaction. And I'll use transaction spans for that. This is a new feature. So I should probably start by searching for where the customer, for all of the times when the customer interacted with this robot through our API. So I can build the query visually. Say I want to search the bot service for all the server spans, type in the bot ID. This is going to be fast because I put an index on robot ID. This is part of my span. Run the query. Latency of that was pretty much the minimum latency that you can get out of CloudWatch Logs. And so this returns all those interactions. Oh, I think I went a little fast there. Oh, yeah, I guess I just showed you that you can actually find and search for. I think I zoomed past a little part of the demo, and it's kind of impossible to go back. It's OK. Yeah, that's probably all right. I'm not too worried about it. Basically, you just search for all the span interactions, and then it'll, yeah, this is worth it, 30 seconds. So I'm searching for the span again, typing in the robot ID. I'm not going to press next this time, hands off. Search for that. Again, it returns the spans. So I can see a bunch of kind of strangeness in here. If you look, I actually have one of the spans shows a 409 status code just in the summary. That means an HTTP conflict. So if I click on that, this is where I thought, yeah. Oh, I guess I'm going to do some more searches. That's right. I'm going to search to see maybe the customer actually accidentally deleted their schedule, because they said, oh, my schedule's gone. You know, we typically don't just lose things. So I should see if they deleted. So I'm looking for the delete API to see if they called that. They didn't, so that's not the right thing. So I can see if they maybe, I need to go back and find when they created the schedule in the first place to see if we messed something up at that time. So I'll search back to see when they created it, and I can see that when they created it, we've returned this HTTP conflict error. Okay, so that's not good. Now these are all traces, so I can click on the trace and see how that span flowed through the whole system, which component it happened on. And now I can, so I'm jumped from the span to the whole trace, and I can see the interaction and drill in and see where we messed up. That's about it. So jumping between spans, analyzing, finding spans, doing needle in the haystack searches, and then being able to jump out to the rest of the telemetry types, like the whole trace. So far in this talk, I've left out one of the most common types of chaos agents that exist in our systems. That's changes. Things that I do that I cause to break because I made a mistake. That's one of the big ones. So the changes are infrastructure changes, code deployments, feature flags, all those types of things. How do we find those? So let's take another example and just troubleshoot. We're going to go through the checklist. We're going to move kind of quickly. So here we're starting the investigation in the bot forge service. So I've skipped the part where I had to navigate to the component that has the problem. Okay, so back up on the board. We have a checklist. We're looking for what happened. There is no traffic spike. I can see that right away. It does seem like we've hit a wall. Why did I say that? I don't remember why I said that we've hit a wall, why we've run out of something. Really cannot remember, but I don't think it's important. So we click on dependencies to see kind of continue navigating from here to see what might be the problem. And sure enough, there's a dependency of the bot forge service that's returning errors. So this is, again, now I filled in the dependency to show, yeah, there's probably a problem with the dependency. Oh, and so the animation just popped up early. The reason I said that we might have run out of something is because the errors we're getting back from DynamoDB here are errors, not faults. What that means is we're calling DynamoDB wrong. And when we get a 400 back from DynamoDB, that's either we just called it wrong, or it could mean that we're getting throttled. We've exceeded our quota. So that could be this. So that's why, well, maybe the errors mean we're getting throttled. And so that's why we may have hit some limit. OK, let's keep investigating. I'm going to click on those errors to zoom in and see what those errors really are, because they could be a lot of different things. Click on that. Let's pick one of the spans this time, because we need to try to drill in to see what any one of these is all about. Click on it, get to the trace thing. I already know where I am, so let's look at the bot config table, see what's coming from there. And the exception says, this is not actually me getting throttled. This is me getting access denied. And access denied does not happen spontaneously. So that seems like we've made a change with very high confidence. OK, something got changed somewhere. It could be a couple places that we made that change. Let's figure out why and where. I'm going to jump over to CloudTrail. CloudTrail records every interaction that you have with every AWS service, especially control plane events, like when you mutate things. So I don't remember the syntax in CloudTrail Lake, so I'm just going to ask it to build a query for me, generate a query, show me all the things, the management events, not data plane events, mutating, OK, et cetera. Great, runs a query for me. Run it. This should filter out all the other noisy events that I don't need and don't care about. Click on query results. OK, except there still is a lot of noise. I'm seeing a lot of these update instance information start query. Those are clearly not interesting. That's not what I'm looking for. Now I could continue revising the query to filter ask it, OK, generate the query again, filter these out, filter this out. But actually what I scrolled past, you may have seen it scroll by, is this new summarize results button. So I can say, hey, actually CloudTrail, take all those noisy results, just summarize, tell me kind of what's in there at a glance. Nice way of asking it to do work. Now what it did in that sentence was, I found a bunch of this noise, and one put resource policy on a DynamoDB table called botconfig. Well, guess what table I was just looking at that had the problem? Botconfig. Put resource policy. That sounds like access denied. So great, I found the issue. So this is an important thing about being able to search for and find changes very quickly without having to sift through and search and search and search. We can bring you changes to your AWS resources easily because we see those happen. But when you use some other tool to do code deployments, just make sure that you can see changes from that are relevant to an investigation easily. OK, let's speed all this up. We were searching this whole time for 5 different things, 5 mitigatable causes, things that we could do something about. But I'm going to show you a new capability of CloudWatch that speeds up this whole process, does these things, but helps you move faster. Now, I mentioned that part of the nice property of this kind of finding the causes algorithm is that you can parallelize. You can get more help from more coworkers if it's a more serious issue and follow all of the leads separately. Well, now CloudWatch has a tool that helps you parallelize even more. It has an AI agent that you can ask to do investigations and help you sift through all your telemetry, your topology, and bring you suggestions about things that might have happened. I'm just going to show you. So let's do that investigation again. This is the investigation that we were just looking at. But here I'm actually starting from the entry point. I'm starting from the robot service. This is the top level microservice. I say, let's figure this out. So I'm in application signals looking at the bot service, the gateway, if you will. And I'm looking at it. I'm saying, hey, there's clearly something going on here. I got paged. There's some problem. Had a useful starting point. Looking at the APIs, I can see, yeah, this one put bot ID that's like a configuration API of mine. That's the problem. I'm just going to click on investigate. Investigate, I'll probably type in a name for the investigation, bot service investigation, and say go. Find the metric, the SLO metric that I started from. And then we'll pull up the investigation. This is the new investigation helper in kind of Q, Amazon Q developer. So it's going to bring me a bunch of suggestions. It's going to be searching quickly in the background, following all these 5 leads, the 5 things that we're looking for. It's looking for all of them. And here already it found something in bot schedule service. Again, this is a dependency of bot service. So it's already chasing the topology down to look for related things that could explain it, kind of following causal pathways. Okay, so I'll continue on. It's looking at bot schedule, it's kind of remote dependencies. I can say accept, which is just saying it's bringing me things that it finds, and I can say whether it's relevant or I can discard things. This found an access denied message in a log right away, so that was actually, I could probably just stop there. It found me a bunch of things. I can just say, okay, I'm going to keep scanning. This actually found an interaction with that specific bot forward service microservice in DynamoDB, noticing these errors. Already found that, sifted through all my telemetry, keeps finding more, keeps finding more. Can say show more related to this DynamoDB interaction, and finds more. And actually, what do you know? So it's finding more errors talking to DynamoDB. And then it found a change event. A thing that I did in CloudTrail. It found it in CloudTrail. It found the thing that I changed related to putting resource policy. Okay, all very useful. So it actually has already helped me sift through and helped. It kind of was somebody helping me, parallelizing, going on all the fact finding. It's fantastic. If I say accept, well, the other type of thing that this experience does, in helping me troubleshoot, it kind of found a log insights query. That seems relevant. Some errors. I'm going to just go ahead and accept that. Getting some access denied. Okay. One thing that it also does is it produces hypotheses. So this is the findings. This is the thing that I've ruled in as like very interesting and relevant to the investigation. Now it also has this hypotheses that it'll fill in. Say, here's what I actually think was going on. Like now that I've looked at all the findings that you have accepted, here's what I actually think is happening. Just want to zoom into what the final hypothesis was that it gave me. So it's pretty interesting. In this example, it said, the bot forward service experienced significant fault rates due to access denied errors when attempting to perform put item operations on the bot config DynamoDB table. So it really found all the way, chased all of my dependencies and everything to find the interaction and explain to me what is wrong with that interaction. Then it explains the trigger. It says these errors were caused by an update to the resource-based policy on the bot config table, which explicitly denied access to the storage. Okay, great. That's the thing that I need to go fix. And then it also gives me afterward a little bit of an impact summary. It says this propagated to dependent services like bot service and because of the read and write problems on the config table. Fantastic findings. Absolutely fantastic. Now I think it's also funny because it also, then it says what to do. So here's what maybe you might consider doing. In some cases, this will recommend actual AWS Systems Manager runbooks that you can say click and it'll make a change. In other cases, it gives you more general advice. And this says, hey, review those recent changes you made and undo them because they're probably not right. You should also audit your IAM roles to see if you have anything else you messed up. And this is the part that when I was running this demo, I actually laughed out loud. Because what this thing was doing was actually wagging a finger at me saying, what are you doing making these random ClickOps changes, breaking your tables? Don't even, exactly. It's like, stop doing that. Implement an actual change control policy. It's fantastic. I just thought that was really neat. Okay, in conclusion, we went through 5 things that you can do when you're troubleshooting, 5 things to look for that will explain the root cause. I talked about how to navigate, the importance of connectivity and navigation between infrastructure, traces, your application, how to get an information sent and just kind of a greedy algorithm, investigate, navigate, and then move on. I also talked about how to drill down, dig down deep into the data and slice and dice things by every amount of instrumentation that's in the span and in your infrastructure. And then we talked about how to apply this approach when you troubleshoot as a team. So I hope that these tools and mental cognitive strategies and tactics will help your next outage be a lot shorter. Please fill out the survey. These help us make these talks better year over year. And have a great rest of your reInvent.